Sound waves, again, this is really important, this is why I'm repeating a lot. Sound waves are mechanical longitudinal waves that carry energy from one place to one place. The waves are created by vibrations of moving objects. It's a series of compression and rarefaction. That's another definition of the wave. So sound wave is a series of compression and rarefaction, and sound travels in a straight line. Remember, sound waves are mechanical longitudinal waves. In the medium, we said sound, we can also define sound as a series of compression and rarefaction. What is compression and what is rarefaction? These questions. Compression, a high pressure region or a region of increased particle density caused by forward movement of the particles. What is rarefaction? Those are areas in the medium or regions of low pressure and low density. And this is what we have, the backward movement of the sound beam. Okay, so here this illustration just to explain what do we mean by areas of high density and high pressure. You see there are so many particles here. Those are areas of high density, high pressure, and narrow molecular spaces. The spaces between the particles, or the distance is very small. So in these areas here, sound will move forward. This is compression. There are areas of hardly anything, rarely anything, low density, low pressure, wide molecular spaces, and that's rarefaction. Remember, sound needs a medium to travel. The medium determines the speed of sound. Okay, we say sound needs a deformable medium, and sound does not travel in a vacuum. The medium that sound needs to travel determines the speed of sound. In the medium, there are two parameters that are responsible for determining the speed of sound. What are those? Density and stiffness. Stiffness has more effect on the speed of sound. Again, this is really important here, okay? Sound needs a medium to travel. Sound does not travel in a vacuum. The medium determines the speed of sound. In the medium, there are two things or two parameters that determines the speed of sound: density and stiffness. Stiffness has more effect on the speed of sound, and stiffness is also known as bulk modulus. Sound is mechanical longitudinal waves. Sound carry energy, not matter. It doesn't carry the matter. It carries energy from place to place. Sound is created by vibration of moving objects. And sound, we can also define it as a series of compression and rarefactions. Sound needs a medium to travel, and sound cannot travel through the vacuum. And as I said earlier, the medium determines the speed of sound. And in the medium, there are two factors that determines the speed of sound. What are those two? Stiffness and density. And out of the two, stiffness has more effect on the speed of sound, and stiffness is also known as bulk modulus. Okay, sound waves can be continuous or pulse wave. So what determines whether sound should run continuously or runs interrupted by gaps in time? That's pulse wave. This is determined by the transducer. What do we mean by this? So let's open the continuous wave transducer. We have so many crystals inside. These crystals, regardless of the number, they will be of two types or two kinds. One type sends the pulses inside the soft tissue. The other one will receive the retaining echoes. So this is why the wave runs continuously, no gaps in time. Whereas pulse wave transducer, if you open it, it has so many crystals inside, they're all going to be of the same type. There is only one type of crystals. So all the crystals will turn on and send pulses inside the soft tissue, turn off, and receive the retaining echoes, okay? So it alternates between sending and receiving because there is only one type, and this one kind or one type alternates between sending and receiving, and this is why we have gaps in time. So the crystals will turn on to send the pulses and turn off to receive the retaining echoes. The off time is also known as the receiving time, the listening time, the depth of view, okay? So that gap in time is when the echoes are coming back. Okay, so the type of crystal alternate between on and off, sending and receiving, talking and listening. Okay, that's why pulse wave is interrupted with gaps in time. Okay, let's learn about sound or some properties of the sound wave. We will focus now on continuous wave. Okay, so we have 7 acoustic parameters for continuous wave: wavelengths, frequency, period, propagation speed, amplitude, power, and intensity. And acoustic parameters for pulse wave will be pulse repetition frequency, pulse repetition period, pulse duration, spatial pulse length, and duty factor. 5 parameters. So we have 7 parameters for continuous wave, 5 parameters for pulse wave. Let's just focus on continuous wave for now. So the 7 acoustic parameters for pulse wave, for continuous wave, are wavelengths, frequency, period, propagation speed, amplitude, intensity, and power. Okay? To do well on this test, you have to know 5 things about each and every parameter. What are the 5 things we need to know? Definition. Okay, what is it? What is frequency? What are the units we use for frequency, for example? So you have to know definition, units. Is it determined by the sound source or the medium? Can the sonographer change it or cannot? And what's the typical value of this parameter? And remember these things here to help you remember definitions and units. Okay, F, frequency. F in physics is a number, so you see F is a number of cycles per second, and when we have pulse repetition frequency, F again is a number of pulses. So frequency is a number, F is a number, just to help you remember definitions. Okay, frequency is a number of what? Number of cycles in 1 second. We're counting how many waves we have in 1 second, how many cycles we have in 1 second. Okay, and period is always time, and wavelength, length means distance. Okay, so that's the distance that one wave occupies in space, and period is the time it took for one complete cycle to occur. Okay, and C is what we use for propagation speed. And remember, these 3, amplitude, intensity, and power, those 3 are for the bigness of the wave. They determine how big or how small the wave is. Okay, so we have 7 parameters: frequency, period, wavelengths, propagation speed, amplitude, intensity, and power. F is a number, so frequency is a number of cycles per second. Period is time, time for one complete cycle to occur. Wavelength, length is a distance, the distance that one wave occupies in space. Okay, and the speed is the speed at which sound travels in the medium. Amplitude, intensity, and power are the 3 parameters that describe bigness of the wave. Hello, and welcome to my ultrasound physics review course. I'm Dr. Sanaa Mustafa. I'll be teaching you this review course, and in this course I will focus exactly on the material you need to pass your SPI physics test. I don't give you unnecessary information. I teach you well and go straight to the point and give you the information you require to fully understand the concepts of ultrasound physics and pass your SPI exam. This course will enable you to understand the concepts of ultrasound physics and not just memorize facts. Every question on this test really requires critical thinking. You won't be able to do so unless you really understand the concepts and understand your basics. So in this course, I'm trying to make physics very easy for you. We'll break it down to very small doses that we can tolerate and understand, and hopefully pass with very high grades. I have very high score rates. One of my students got 692 out of 700. So hopefully one of you will get 700 out of 700. Okay, so welcome to the course and let's start. Frequency. Frequency is the number of waves in 1 second. Number of cycles. Remember F, frequency, F, it has to be a number of something. So frequency is the number of waves or number of cycles in 1 second. The frequency of an audible sound is called the pitch of the sound, and is determined only by the ultrasound system, not by the medium. If frequency doubles, wavelengths halves. Okay, frequency and period are inversely proportional. Frequency and wavelengths are inversely proportional. they do the opposite. Double, what's the opposite of double? Halves, okay? So if I double my frequency, what happens to the wavelengths? It's cut into a half. What kind of units we use for frequency? Hertz, kilohertz, megahertz. What's a hertz? A hertz is 1 cycle in a second. So if you have in 1 second, I have only 1 cycle, that's a hertz. If I have 1,000 cycles, that's a kilohertz. If we have 1 million cycles in 1 second, that's a megahertz. Frequency cannot be changed by the sonographer, and frequency is determined by the source. Okay, and frequency affects penetration and axial resolution. Resolution depends on the wavelengths. Okay, so if you have a very small wavelengths, we will have very good resolution, and that of course happens with high frequency. We get the smaller wavelengths. Okay, so high frequency has very good resolution, but it has very bad penetration. We'll talk about that in a minute. Frequency is the number of cycles that occur in 1 second. Units are cycles per second, or hertz, megahertz, or kilohertz. And what we use for diagnostic medical sonography, 2 to 15 megahertz. Frequency equals 1 over period. Frequency is determined by the transducer, by the source. Frequency cannot be changed by the sonographer. And remember, we use for superficial structures, we use high frequency transducer. For deep structures, we use low frequency transducers. Okay, do you know why? Okay, if you don't know, now you will know. Okay, why for superficial structures we use high frequency? Like if I want to scan thyroid or testicular examination or peripheral blood vessels, I use the linear transducer, high frequency transducer. If I'm trying to scan deep structures like abdominal examinations, I use a very low frequency transducer, the curvilinear or the convex transducer. Why? Okay. Hello and welcome to my ultrasound physics review course. I'm Dr. Sanaa Mustafa. I'll be teaching you this review course, and in this course I will focus exactly on the material you need to pass your SPI physics test. I don't give you unnecessary information. I teach you well and go straight to the point and give you the information you require to fully understand the concepts of ultrasound physics and pass your SPI exam. This course will enable you to understand the concepts of ultrasound physics and not just memorize facts. Every question on this test really requires critical thinking. You won't be able to do so unless you really understand the concepts and understand your basics. So in this course, I'm trying to make physics very easy for you. We'll break it down to very small doses that we can tolerate and understand, and hopefully pass with very high grades. I have very high score rates. One of my students got 692 out of 700, so hopefully one of you will get 700 out of 700. Okay, so welcome to the course and let's start. Okay, let's start with the textbook. Understanding Ultrasound Physics by Sidney Edelman is an excellent book for learning and understanding ultrasound physics, and it prepares you very well for the SPI exam. I highly recommend this book. It's very easy to read, very easy to understand, and it has great questions at the end of every chapter. It has total of 24 chapters. At the end of every chapter you have very good questions, and at the end of the book you have many questions to practice for the SPI exam. I highly recommend this book, so if you don't have one, make sure you get one. Okay, here are some frequencies, spectrum of sounds, like for example infrasound. What's the frequency? Less than 20 hertz. Audible sounds, that's between 20 hertz and 20,000 hertz or 20 kilohertz. And ultrasound is greater than 20 kilohertz. And what kind of frequencies we use in diagnostic medical sonography again? Like say, I'm repeating this a lot. It's a test question. It's going to be on the board exam, okay? What's the frequency used in diagnostic medical sonography? 2 to 15 megahertz. Why is frequency important in diagnostic sonography? Frequency is very important in sonography because it affects penetration and the image quality. High frequency has less penetration, more attenuation, and that's why we use it for superficial structures. Low frequency has more penetration, less attenuation, and that's why we use it for deeper structures. Okay, so if you see here, this is low frequency. See, what is attenuation? Attenuation is weakening of the sound as you go deeper and deeper and deeper in the tissue. As sound is traveling in your tissue, it gets weaker and weaker. It loses its amplitude and intensity. Frequency, of course, stays the same, okay? Low will stay low and high will stay high. Attenuation does not affect the frequency, but what it reduces the amplitude and the intensity. Look at these diagrams here. When it is low frequency, like the top one here, is gradually getting weaker. So you have, it really became a flat line very deep in the tissue. So low frequency has less attenuation, more penetration, and that's why we use it for deep structure. Whereas in the second diagram here, you see, high frequency attenuates very quick and it dies very quick, very in the superficial layers below the skin, okay? So high frequency has more attenuation, less penetration, and that's the reason why we use it for superficial structures. Like, for example, if I'm using scanning blood vessels, that's just peripheral blood vessels. Below the skin, they're very superficial. We use linear transducer. Okay, very good resolution, nice images. This is where we use high frequency, and it has very good resolution, but we can use it for deeper structures. Why? Because it attenuates fast and penetrates less. Less penetration with high frequency, okay? High frequency gives you good resolution, good images, but it has more attenuation and less penetration. That's a bad thing about high frequency. It has more attenuation and less penetration. So it's only used for superficial structure. How can I use high frequency for deeper structures? This is only possible if we use invasive transducer or intracavitarial transducers like the endovag, the endorectal, the transesophageal, transcatheter. In these transducers they build those transducers with a very long handle. And they put the PZT at the tip of that long handle. And they take the long handle with the PZT and insert it inside the body through the oral cavity or transvaginal or transrectal, okay? Where they took the crystals close to the structure you want to image. Like in case of endovag, you're taking the crystals close to the uterus, so you don't have to worry about the distance sound is going to travel and the attenuation and all that. And because the crystals are next to the uterus, we can use very, very high frequency, highest frequency to scan deep structure. It's only possible with invasive or intracavitarial transducers, okay? But yes, with regular transducers, high frequencies for superficial structures, low frequencies for deep structures.